All right, let's go ahead and get started. Last time we started with linear bandits, or we ended with linear bandits, and we're going to continue that now and hopefully get through it by the end of today's lecture. So, to remind you, the setting is, for t equals 1, 2, ... The algorithm picks it, or let's drop index notation, because we can do that now that we have vectors. So actually the notation gets a little nicer. Xt in x, and then nature reveals yt equal to xt transpose theta star plus eta t, where eta t we're going to assume is normal 0, 1. And theta star is unknown, in RD unknown, and but x, which is just some set of vectors, some subset of RD, is known. And again, for the pure exploration portion of this, we're going to assume that the best arm is unique. And again, to remind you of the motivation here, it's like you go to Netflix, you have some preference vector that is describing your preferences over movies or whatever, and xt is a particular movie with different attributes or features like genre or actors or whatever, and the result of whether you like it or don't like it, rated 1 to 5 stars or whatever, is modeled as this linear relationship between the feature vector of the movie and your preferences, which are theta star, plus some noise. Okay, and we talked a little bit about last time about how this isn't the perfect model if you have sort of click-through information of 0, 1, but I'm sort of brushing this under the rug and claiming that this can be dealt with by using sort of a logistic link function and not really talking about it during this lecture.
So what do you mean by best arm here? Is it one of the x's, or?
Yeah, so I'm going to define x star as being argmax x in x as x theta star. Okay, and so this is the best arm. This is, so in a best arm context, this is like you have many, many materials. You say all the peptides of length 12. We can extract different feature vectors from these peptides. And so these are all into some d-dimensional feature space. There's one material that has, that optimizes some property, and that is x star, and I'm trying to find it. Okay, and that's because that's the one I'm going to bring to market. Okay, and so what we did last time is we said that taking a pause on this problem for a moment, if we just had a finite data set of xi, yi pairs, 1 to tau, this is RD and R, according to this model, where, say, yi is equal to xi theta star plus eta I. Then I can write this, I can stack these vectors up, where x is now x1, x tau, like that. Y, same thing. y1, y tau. And then if eta, I stack the etas, then I can say that y is equal to x theta star plus eta, where eta is this Gaussian 0 identity vector. Okay? And furthermore, we showed that under this model that if you compute theta hat, if I compute the least squares estimator, or the maximum likelihood estimate, we find, so that's just argmin theta x theta minus y, that has a solution, assuming that x transpose x is invertible, x transpose y, which we then plug in our value of y, and we find that this is just going to be equal to theta star plus x transpose x inverse x transpose eta. Because eta is a Gaussian vector, Gaussian zero identity distributed vector, independent components, we see that the covariance of theta hat is just going to be given by this matrix, like we did last time. So what we conclude is that theta hat minus theta star is drawn IID from some normal distribution of mean 0 with covariance x transpose x inverse. Okay, and so the point here is that depending on what x's are chosen in this regression, we're going to have a different covariance, meaning the shape of our uncertainty will depend on whatever covariance x we chose to actually perform this regression. And most importantly, we can decide this ahead of time, right? The covariance, the distribution, the uncertainty with respect to how bad is my estimate from theta hat to theta star does not depend on the true theta star. This is a remarkable fact of linear estimation, and it allows us to plan. Meaning that if I want to, I can basically predict what my uncertainty will be in any given direction even before I've seen the y's. Just given the x's, I can predict what the uncertainty is going to be. Even though I can't predict what theta star is going to be, I can predict what the uncertainty is going to be because theta hat is unbiased, meaning its expectation is equal to theta star, and the uncertainty, meaning how far away is theta hat from theta star in any given direction, is given by this covariance matrix. Now, most importantly here, though, is that we can do something very nice where for any z, we have, by the same rules of Gaussian distributions, we have that if I inner product z with theta hat minus theta star, now z is a fixed vector in RD. It's any z. It may have nothing to do with x's. It's just some vector in RD. It's going to be distributed. If theta hat minus theta star is distributed as a Gaussian with this covariance, then the inner product between z and theta hat minus theta star is going to also be Gaussian, mean 0, but now with covariance z transpose x transpose x inverse z. Okay, this is getting really good. Because what we did on the first day of class, which was yesterday, was showed that if a Gaussian vector, or if you had a Gaussian random variable with mean 0 and variance sigma squared, then we knew that we can build a confidence bound that was like square root of 2 sigma squared log 1 over delta. And so what we can conclude, if we just call this sigma squared, then we know that the probability that z theta hat minus theta star greater than or equal to 2 sigma squared log 1 over delta is less than or equal to delta. Okay, this is true for any Gaussian random variable. And this just happens to be a Gaussian random variable with variance z transpose x inverse z. Something pretty complicated, but something that we can get a handle on. I'm going to write this a different way, as I can write this guy as a slightly different notation. So rewrite this as saying that with probability, 1 minus delta, I'm going to do a two-sided. So I don't want just this. I'm going to do this and then minus this. So a two-sided confidence interval. And to do that, I'm going to put a 2 here. So it'll still hold probably 1 minus delta. And I'll have that z. Probably a 1 minus delta, absolute value of z theta hat minus theta star is less than or equal to square root of, I'm going to plug this in, z transpose x inverse z times square root of 2 log 2 over delta. Okay. Now this quantity, I'm going to use some notation here. The notation is for any vector x or whatever, x transpose a x is equal to x squared. Okay? This is sometimes known as the Mahalanobis distance or norm. Basically, it is just stretching different dimensions in different directions. But I'm defining this as this quantity. So anytime you see a norm of x squared sub a, I actually just mean this. And just a little simplifying notation so that I can then write this as z x transpose x inverse square root of 2 log 2 over delta. Okay, that'll be important. So, as I alluded to earlier, different choices of x transpose x will result in different covariances, in different shape of uncertainty. And you can see it already just in this. So for any direction z that I look in, basically the uncertainty is being scaled in that direction by x transpose x inverse. Meaning if I had a lot of x's in that direction z, this norm with respect to x transpose x inverse will be very large, or x transpose x will be very large in that direction, and therefore z transpose x quantity inverse z will be very small. Again, the picture that I drew last time was if you have if your x's looked like this, then you have a lot of x's in this direction. And so that if you had some vector z, because I don't have many x's in this direction, my confidence interval, if this is some vector z, would be very, very big, because I don't have a lot of x's to cancel out the direction in that direction z. However, if I look in this direction, I have lots of x's. I have lots of energy going in that direction. Because this x transpose x, recall, is just x transpose x is equal to the sum of xi transpose. So if I put a z on both sides, z transpose x transpose x z equal to z x transpose x inverse is equal to squared is equal to essentially z going on both sides, but this is the inverse, and so it's difficult to picture. That was a bad example going down this road. But I have a lot of energy in this direction, and so the confidence interval in this direction z will actually be very small. Because in that direction, if I were to do this eigenvalue decomposition and rotate all the axes and everything, picturing PCA in your head, you'd have a very small confidence interval in this direction because you have a lot of data in that direction. And we're going to use this in our algorithm to plan for uncertainty. So in particular, we're interested in a few ways of planning for this. So typically when we have it, so the idea here is that we have these pool of x's, right? We have any vectors of this finite pool we can choose to go and measure. And we know that when we measure them, we can quantify the uncertainty ahead of time, what it will look like. And so given this, you might have different objectives that you may be interested in. But it's very annoying to actually optimize over this discrete set of x's, so integer constraints. And so a lot of times what we do is we approximate for every x transpose x, there exists a lambda in the simplex, which I'm going to notate like that, such that x transpose x is equal to x in x lambda x x transpose all times tau. Because there's tau vectors in big X. That's what I have here. There's tau of these that I chose. And so all I'm doing is I'm saying that for all choices of x I could make, there exists some probability vector on the simplex such that x transpose x is equal to tau, the total number of measurements, times the sum over all lambda x. That's super small, isn't it? Where lambda x is just going to be equal to the number of times x appeared in big X divided by tau. Okay? Now, we can't necessarily go the other direction, meaning that for every lambda, there exists a matrix X such that I can realize it with a finite number tau of measurements. However, if the support of lambda is very small, then I can always round the solution. So for every lambda, I can take tau measurements, like sample according to that lambda, or just round the solution. And then that should be pretty close. And we're going to use this intuition in a second. But often when we're designing our covariance or uncertainty structure, we're going to be choosing lambdas and optimizing over lambdas this way. So just define a lambda as just this object. For any lambda, define the object lambda x, xx transpose. And so if we wanted to go choose measurements, what is the measurement plan that we would make? And so this is called linearly experimental design. And there's different criteria that you could want. If you wanted to minimize, if you chose lambda to min over lambda of max u such that the norm of u is less than or equal to 1 of u transpose A inverse lambda u, then this is going to minimize basically the maximum uncertainty in any direction. Meaning this ellipse is actually going to just be a ball. And that's very nice. A optimal. I'm just listing these off real quick because they're kind of interesting. If you min over lambda to maximize the trace of A lambda inverse, this actually minimizes the expected value of theta hat minus theta star, which is slightly different than this quantity, because it's the trace, it's the sum of the eigenvalues versus the worst case eigenvalue, which came up briefly last time. And most importantly, G optimal is going to be minimize lambda subject to maximizing x in x of x transpose A lambda x inverse. Because what this minimizes is equivalent to minimizing the maximum x in x of expected value squared. Okay. And the reason why I care a lot about this one is because we can actually relate this linear bandit setup to our original bandit setup, right? If we think back to what multivariate bandit was doing, we had individual arms, and we pulled one. Pulling one had no effect on pulling another one. So to model that in this framework, I can have the x's just be canonical vectors of all zeros with a 1 in the ith position. Okay, so I can always put standard bandits into this framework. And under that framework, what this would be doing is I want to choose the lambda in order to maximize the largest confidence interval. So this would be this is equivalent to, in the bandit setting, of just uniformly sampling to minimize the maximum variance. I want to have those confidence intervals all be the same across all the different x's. And that's exactly what we were doing in our action elimination algorithm. At each stage L, we were setting the confidence intervals to be some size of 2 to the minus L. And then we were repeating this, and as we increase L, epsilon L was going down like 2 to the minus L. And you're getting more and more sort of close to the best arm. And so what we want to do, G-optimal seems to be, if we're going to follow that same sort of pursuit, it seems to be exactly what we're trying to do. Okay? Because this is equivalent to, I want to choose my design X such that I minimize the covariance or the largest confidence interval of my X's. Yes?
On the very first line at the top of this board,
Yep.
is that expression supposed to be equal to something? You said there exists lambda such that...
Oh, sorry.
Okay, and on the A optimal line, what is that minimum over on the right-hand side?
Over lambda. So it's
the right-hand side have to do with lambda?
So what I'm going to do is I'm going to sample. It's kind of this analogy here. Once I choose a lambda, I'm going to take tau measurements from it by essentially saying I'm going to measure x, the equivalent, measure given lambda in the simplex and tau in this, pull x exactly the ceiling of lambda x tau times. Okay? And so when I put the expected value of theta hat minus theta star, this theta hat is the result of I'm going to choose a lambda, and given that lambda, I'm going to go and take tau measurements, and then I'm going to construct the least squares estimator. And with respect to the random y's that choice of x's give, this lambda, this choice, if I choose lambda to minimize the trace of A inverse, minimizing lambda to minimize this is equivalent to minimizing this for large enough tau, so that these integer issues go away or just are not relevant. Okay. So for the purposes of this conversation, don't worry about the ceiling. Just imagine tau is large enough so that these integer effects are negligible.
On the E-optimal line, what's this syntax going to?
It's going to min lambda sup u 2 less than or equal to 1 of this guy. Very similar to G-optimal design. It's basically G-optimal with the unit ball. And all these are very useful. The final one I just want to put up here, just for kind of fun, is, because it's something you've already seen, is the log det. Maximize lambda. It's the only maximization problem on here of a lambda. On the other hand, what I could do is I could minimize over lambda of a, the det of a and lambda inverse. I'm using this notation of squared bracket or squared lines as determinant. Sorry. Vertical lines mean determinant in these lectures. And where this comes from is actually, if you think about what the Gaussian density is, so we said that theta hat is equal to this guy. And basically, the covariance of theta hat minus theta star is equal to x transpose x inverse, which is equal to a lambda inverse. And if you compute the entropy of that distribution, the entropy of that distribution is exactly log det of a lambda inverse. And so your d-optimal design is the equivalent of choosing your measurements in order to minimize the entropy of theta hat. Pretty intuitive thing. OK. Now, the big reveal. So this is all very nice. But one of the most famous results in extreme relative design is the Keifa-Wolfowitz theorem. And what it says is that if lambda star is, for any x in RD that spans RD, there exists a lambda star in such that max lambda of, let's call it GD of lambda is equal to GD of lambda star. It's 1, 2. I'll define what these are in a moment. Min lambda FG of lambda is equal to FG lambda star. And 3, the support of lambda star is equal to d plus 1 d over 2. Oh, the most important property. F of g lambda star equal to g d of lambda star is equal to d. And I'm defining this as gd of lambda and this as fg of lambda. So it's the g-optimal design problem and the d-optimal design problem. And Keifa-Wolfowitz says that these two are the same. Minimizing the g-optimal design and maximizing the d-optimal design give exactly, there exists a single vector lambda star that achieves both. The value of them is equal to d. And there exists a lambda star that has support at most d plus 1 d over 2. Okay, regardless of the size of x. This is an amazing theorem, by the way. And it's not at all obvious that g-optimal design is related to d-optimal in any way. This is very surprising. It's very easy to go one way. Going the other way is very hard. And you'll discuss this in section. But really the remarkable thing is that the value is exactly d. And we're going to use this in building confidence bounds. OK, and we'll do that right now. Is there any questions on the statement itself?
Lambda x is?
Lambda x is, well, are you talking about this guy here?
Yeah.
This is delta x.
Sorry, delta x, yeah.
Oh, I introduced another delta. This is a simplex. I'll say triangle. Triangle x, or simplex x, is, in LaTeX, these are all different characters. But this is the simplex, meaning it's just the space of probability vectors.
What is the support of lambda star?
The number of non-zeros.
So it's smaller than d choose 2, right?
Smaller than. Thank you. Yeah, it's at most d plus 1d over 2. And where this comes from is actually, if you think about what A lambda is a convex combination of matrices that are d by d. Symmetric d by d matrices. That means the degrees of freedom are only d plus 1 times d over 2. Is in a vector space of that size. And by Kara-Theodori's theorem, any point in a convex combination, or any point in a convex hole in a vector space of size d can be represented by a convex combination of at most d points in that set. And so since this vector space is of size d plus 1 times d over 2, we get that this is true. OK. This is leading somewhere, I promise. Proposition. If lambda star is the G-optimal is the d plus 1 d over 2 sparse solution G-optimal design solution, and x is pulled lambda x times tau times for some given tau, and we compute theta hat using these, the least squares estimate, then with probability greater or equal to 1 minus delta x theta hat minus theta star less than or equal to x lambda x tau. This is just the number of times I've pulled the x guy times xx transpose inverse times the square root of 2 log 1 over delta. Okay, so I've just sort of rewritten this statement that I have over here just for this particular value of lambda star. So I haven't done anything new. This is just always true for any allocation of lambda. But then, I know this is hard to see. This guy, because I did the ceiling, and is a PSD matrix, I can remove the ceiling because it's in the inverse. And this is less than or equal. So once I remove the inverse, or sorry, once I remove the ceiling, I can pull the tau out because it's just a constant now. And I get 1 over square root of tau times lambda x star xx transpose inverse square root of 2 log 1 over delta. And finally, for this particular x, well, the G-optimal design, by definition, minimizes the maximum x. So x is just one of them. A G-optimal is minimizing the maximum one, and that value is exactly equal to d. This whole thing has to be less than or equal to square root of d. Okay? And so then what we get, since this thing is less than square root of d, the square root of d comes up here, and we get this whole thing is less than or equal to square root of 2d log 1 over delta over tau. Very remarkable result, I think. Oh, and at most, using at most d plus 1 times d over 2 plus tau poles. Right? Because lambda star is a d plus 1 times d over 2 sparse. And by sparse, I mean it has that many non-zeros at most. And so what that means is that when I round this solution, when I take the ceiling of it, I'm incurring at most just d plus 1 times d over 2 more samples. This is in the worst case. And so for this small factor, I can get basically, with just tau total poles, I get something that looks very simple and very nice. And note that in the normal bandit situation, with the standard bandits, this is like pulling every arm tau times, where d there would be equal to n. If I pulled, if I pulled every arm, tau over n times, this would be an equivalent statement because you're in n dimensions there. Okay, so I'll just say one more word about this. This sparsity level of d plus 1 times d over 2, if you're willing to relax this, so if you're willing to have a value that's, say, 2d or 1 plus epsilon d instead of exactly d, then you can get this down to a constant times d, like 2d and 2d here. And so that's kind of a nice little thing. Yeah?
So I'm still trying to understand Keifa Wolfowitz theorem. That big delta of x, I guess I thought it was like a convex hull of x or something.
It's this. Triangle of x is equal to the p in Rx positive, or I can even do 0, 1. Such that the sum over I pi is equal to 1. It's the space of probability vectors. It's the simplest.
That lambda star is not an RD, is that right?
No, it's not an RD. It has dimension the same size as the number of vectors in X. It's a probability distribution over your X's.
Okay, right.
And there's no way this will not get confusing if I'm using delta X. So let me replace this with S for simplex. Sorry. I'm sure there's a million of them on the board now. S is for simplex. Okay. Now, why did we care about this? We care about this because we're going to use this proposition exactly in our algorithm. Yeah?
Proposition, just using at most d plus 1 times d over 2 plus tau full. Is that part of the proposition? Something we concluded from the algebra we just did? Or?
Both. I mean, this is immediate from the fact that lambda star is a d plus 1 d over 2 sparse vector that satisfies this solution. So this lambda star is the one from this proposition. And so it has at most d plus 1 times d over 2 non-zeros. And it takes a value of d. And so if I round it, because I'm taking the ceiling, I'm pulling arm x, lambda x times tau times the ceiling of this. So if I didn't have the ceiling, I'd take at most tau poles. But because these may not be integers, I incur at most 1. And so it's going to be at most d plus 1 times d over 2. Yeah?
So I might be confused. So there's all of the x's in the support get pulled. Is that right? Lambda.
Yes.
Lambda tau many times.
Yes.
And then the statement with probability 1 minus delta is that's a different x, right? So that's any vector z we called it before, right?
Yes, you're absolutely right. For any z, it doesn't matter It doesn't matter what this is. This is just a dummy variable. For any z, it has to be fixed. But yeah, for any fixed z, it's not special to any for any x. I'm sorry. No. Yes, x does have to be. Sorry, that's where I'm going. I'm going to this other place.
In the set x, or it's not in the set x?
For any x in the set x.
But before we had a statement that was quite similar with for any z at all.
Yes. Yes, exactly. So this first line is nothing saying anything. It's just this for any z. That's what this first line is saying. I haven't done anything here. I haven't applied the proposition yet. I haven't applied the proposition yet here. And this is where I apply it. Because I'm saying that this value, by the statement of Keifa-Wolfowitz, is less than or equal to square root of d. Because this value, what g-optimal is doing is it's minimizing this. And this can be written as max x in x of x a lambda inverse. And so if that's the worst case one, and I'm saying that this is less than d, well, this x is just one of them. And so it's not going to be that bad.
So I have some secret theta star, right? And then you say I have this bound on how poorly I'm doing with my estimate.
Mm-hmm.
Now, if I just go ahead and double my theta star, shouldn't you have to double your bound on this inner product?
No. That's a great question. I don't need to do that precisely because of this here. So we have that theta hat minus theta star is equal to this.
Right.
So if I double my theta star, it doesn't change the noise. And where you see that is yi is equal to this value here. If I double my theta star, it doesn't double the noise.
Oh, okay, sure.
So if theta star doubles, you're getting more signal to noise ratio. It only helps.
Yeah. Okay, got it.
Okay, now, our algorithm, we wrote AE1 on the board last time for standard bandits. Because I'm low on time, recall that algorithm. It goes something like, for t equals 1, ... I'll just write it up. Lambda hat L is g-optimal design for x hat L. Epsilon L is equal to 2 to the minus L. Tau L is equal to 2d epsilon L to the minus 2 log 4L squared x over delta. Okay, this should all look very familiar. This is exactly what we had in the previous algorithm, except for now I have a d here. Otherwise, it's identical by design. Pull arm x tau L lambda L times construct theta hat L, and then x hat L plus 1 is equal to x hat L set minus x in x hat L is the exact same condition as last time. Max x prime in x hat L of x prime minus x theta hat L is greater than 2 epsilon L. It's the exact same condition as last time. Okay? The only thing I've changed from last algorithm to this algorithm is now I'm changing what arms I'm sampling. Instead of sampling uniformly at random, I'm going to sample according to this G-optimal design. And what I can claim, which is not difficult to prove, given this, once you have this proposition, if you define the event XL equal to we have that big cup over all L, big cup over all X in big X of EXL complement is less than or equal to delta. So you'll note that this is exactly the same event as defined as last time, right? The difference between the empirical mean and the truth of X, so this is like the deviation of my estimate of the reward of X is less than epsilon L at every round. And you can prove that this is true by very almost identical steps. The only issue, the only sort of fine point that you have to worry about is that at each time in this set, X hat L is now a random set. It is not a fixed thing you can condition on, like we did last time. But all you need to do is you condition on the value of X hat L, and for any X hat L, any fixed set X hat L, the only noise that's entering the system, uncertainty, are the independent realizations of the noise, which are, of course, independent of X hat L, and so there's no issue. I know that was a lot, but if you try to go through the proof, you'll get to this step, and that hint will get you going. OK. Now, all I want to do now is show you that the regret bound is something. Because again, it's basically identical to the proof yesterday after the first step. So I want to get you started on that, and then you can finish it. So again, we have the regret the number of times we play a suboptimal arm with gap delta x, where delta x is defined as x star minus x theta star, exactly as analogous to the standard multivariate Bandit setting. And then we're going to do the same trick over all L, but only up to now log 2 of 8 delta inverse, where that's the minimum gap. And then again, we get this 8 epsilon L. But now we have this d plus 1 d over 2 plus tau L. So the only difference between the last proof that we did yesterday and this proof is that we've got this extra factor here, which comes from the fact that we may have oversampled a little bit. But every time we sample, we're only sampling within x hat L. And so we're getting very small regret, because we're only pulling arms that are still good. So you can simplify this through exactly the same steps as yesterday. It's literally line by line. The only difference was the extra factor of d, because it's the only difference between tau L. And at the end, we get something that, ignoring the factor of d that's not hitting the t, of nu t plus d over gap max of nu log x log nu. This should all look familiar from last time, over delta. Now looking at this, we immediately get a regret bound by playing the exact same tricks as setting delta equals to 1 over t. and by optimizing over nu. So when nu is equal to 0, because this holds for any nu, just like last time, this implies that RT is equal to less than or equal to d times log the cardinality of the number of arms times t over delta. But also, we get a data-independent bound, or a gap-independent bound, just like last time, that now scales like d times t times log x t with different constants c. Okay? So I promise you, if you go through these sequence of steps, you'll get this using the exact same proof. Yeah?
Wasn't the entire reason we moved to these feature vectors was to eliminate the dependence on the site of x?
Great question. Very, very good question. So what he's saying is that if x is very, very large, this could be very, very bad. Because I'm still, even though it's still in the logarithm, which is, reasonable, greatly reduces the size of it, but if x is very, very large, like infinite, this is kind of a problem. And so to solve this problem, what you can do, say, if you have, let's say all your x's lived on the unit sphere, then what you do is basically you do a cover. You basically do candidate x's. You just like randomly sample your x's from this space in a fine enough point. And you can show that if this is a fine enough grid or a fine enough sort of covering, then you can greatly, the error incurred by not having every x is negligible.
You lose some of the geometric properties of the sphere when you do that. Like you can't go over the actual surface of the sphere.
And so, yes, that's accurate. And so over time, you have to refine this grid as going on. But I promise you, it can be done. And it's actually not an issue. And in fact, everywhere you see a log x, I can replace with d, an extra factor of d. Because this covering a sphere in d dimensions with an epsilon net is about 1 over epsilon to the d. And so that you incur this additional factor of d, and you can remove the dependence on the number of x's. OK. Good news, bad news. The good news is if we think back to this morning when we were just going over lower bounds, if we consider the canonical vectors, the standard multi-arm bandit setting, where the ith arm is just all zeros except for a 1 in the ith position, then this is great. Because then this is square root of n times t log nt. Right? That's exactly what we got for the other algorithm. And we argue that that was basically minimax optimal up to log factors. Because we proved a lower bound that was square root of nt, or we showed, I put it on the board, I claimed it. And now it seems to be tight in that regime. So that's a good news. The bad news is in that same regime for these standard multi-arm bandit setting, what we're getting here is d over gap. And where gap is the min gap. Right? And so if we recall to this morning, what the regret bound we got yesterday was log t times the sum of inverse gaps. Right? Yesterday morning, for multi-arm bandits, we got the regret bound was log t 1 over delta I. And what this is saying, if it's d over delta, that's the equivalent of saying log t times n over min gap. That's very bad. It means that we're just pulling every arm sort of uniformly at random. Well, in some sense. We're treating the different arms are not actually being, the fact that they're different means is not really being respected here. It means this algorithm is not taking advantage of the geometry of the problem to the best degree it can. And so, and just as an aside, if we run this algorithm for pure exploration, we'll get something that's exactly d over min gap squared, which is no better than just uniform exploration, meaning not being adaptive at all. And so, it's good news, bad news. in that the good news is that it really is minimax optimal for actually a large number of action sets. This is not actually that bad of a bound. However, there's many sort of situations if you want a gap-dependent bound, if we move away from worst case, this bound is actually very bad. And it turns out that this is an open problem. Getting a bound that's actually gap-dependent, that has an optimal gap dependence on the regret with logarithmic log t, that's finite time, there does not exist an algorithm known for that. And so very much, I wanted to show this because there's still open problems in Bandits, even for this simplest of problem. Right? Ideally, we'd like to get to a place where we are running neural networks and doing Bandits on neural networks where our parameters are moving all around. There's hundreds of millions of them. But even for this simplest linear Bandit setup, there are still open questions. And I encourage you to track these down. How to fix this? To fix this problem, to get a more gap-dependent bound, we really need to start thinking about pure expiration. Right? Because that seemed to be the biggest sort of culprit here, that it's most offensive that if you run this algorithm for pure expiration, it gets something no worse than just running goptimal once before the start of the game and sampling non-adaptively according to that. That seems like a problem. And so what we really need to do is think about what we're doing. Oh, and by the way, last time I claimed that our algorithm, our elimination algorithm, was suboptimal, but UCB, an algorithm that used optimism, somehow came to save the day and gave us this optimal constants and things. That is not the case here. Here, to remove the fact that this has such a poor gap dependence, this algorithm that's only playing arms that are getting better and better and better, meaning closer and closer to the gap, what's happening is if you started with arms that are like this, if theta star is in this direction, what this means is that this algorithm, x hat L, the way that x hat L is really evolving over time is this is x hat 1, let's say, and then this is going to be x hat 2, and x hat 3, and x hat 4, x hat 5, and so on. And so what's going on is this algorithm is only playing, it's basically converging to vectors, only playing vectors that are in the direction of theta star. But this is quite a problem because what I really want to do is figure out this is not actually what I want to solve. Because what I actually need to solve, what I need to show is that x star minus x theta star is greater than 0 for all x. If someone told me what the vector x star was, I would just need to verify that this was true. And how should I measure it in order to do that? And so one way of thinking about this is if I have, say, feature vectors that look like, x's that have like this, and theta star was in this direction, then in order to do best arm identification, basically I should think about the regions. What does this condition say? Basically what this condition says is that anytime theta star would live in this region, this is the best arm. Anytime theta star lives in this region, this is the best arm. And anytime in this region, this is the best arm. So if we consider theta star to be this vector, say E1, then all we really need to do is get the confidence interval. We need to define this confidence set. Like I said, we can choose our x's in order to shape our confidence. And we need to get this confidence interval so that it's completely enclosed inside this interval. But to do that, what geoptimal design is doing is it's sampling more and more in the direction of theta star. So if I had a bunch of x's out here, whatever, more vectors like this, basically it will converge on just pulling these two arms. But because the gap is so tiny between this one and this one, it's going to concentrate all its energy on these. It will take forever to actually find the difference between whether this one is bigger than this one, just using these kind of confidence intervals. But really, all I needed was to get this red sphere, this red confidence set, fully inside this set. And one way of doing that would be just to measure in this direction. Use this x. Because this x, if I measure a lot in this direction, that will squeeze the confidence down in this direction. And this can end up being a far, far more efficient design. And so recently, we developed algorithms in order to do this that can get within a constant factor or a log factor of the optimal pure expiration, which then can lead to towards more things that are regret optimal with respect to gap dependence. But there's still much more work to do for linear bandits. But it's one story that where optimism was such a winning strategy in stranded multi-arm bandits. The story for linear bandits, what I want you to take away from this is that you must plan. You can't just follow your nose. You have to plan with optimal design. You have to sort of think about what you've measured, where you want to go, and you need to sit back and think about where I should measure in order to achieve some goal. And we'll talk next time about adversarial bandits. Thank you.